Hello dear friends, welcome my channels. Today's discussions general relativity, stress, energy, momentum, tensors. So friends, general relativity are in the part number 1 A equivalence principle. Principle. Number B, tangent space. So friends, part of the general relativity is equivalence principle, tangent space, Newton-Cartan theory, curved Newtonian gravity, curvature, energy momentum tensor, Einstein field equations. Einstein field equations are mu nu minus half r g mu nu plus lambda g mu nu 8 pi g c to the power 4 t mu nu. So friends, this is the and this is t mu nu is the energy momentum tensors. So friends, today's discussions is energy momentum tensors. Friends, I will discuss all topic like equivalence principle, tangent space, different video I will publish because all are very large, and try to clear all this topic try to clear this topic nicely. Let's start our discussions. So friends, we know the Poisson's equation. Nabla square phi equals to 4 pi g rho. So friends, we know this is the Poisson's equations, and this value is equals to these equations r double zero is equal to 4 pi g rho. This is this equation is space time curvature. This equation is space time curvature, and this is Ricci tensors. This tensors is Ricci tensors. So we can write this way. So friends, we get equations r0 0 0 0 0 0 0. This is the equations. We get these equations. Now this is the equations. We get these equations from Poisson equations. We represent it as a matrix form. Now this equation not work in general relativity. These equations, it is not work in general relativity, and this is r0 0 the setting the 0 0 component of the this is setting the 0 0 component of the Ricci tensor is proportional to the rho. R00 is proportional to the rho, directly proportional to the rho. Mass density is not Lorentz invariant because this equation is not it is not work in general relativity because mass density is not Lorentz invariant. It is not a tensor. So friends, mass density is not Lorentz invariant. So friends, it is not a tensor. If we look at this same setup in a frame where the volume is moving, the volume could be length contracted to be half its size. Suppose it is del x, so it is contracted and half of del x. It's become half of del x. So volume could be length contracted to be half its size, meaning the mass density in the moving frame will double in size. Mass density is double in size. Here mass density is m by v is rho, and mass density is m divided by half v is equal to 2 rho. So double in size. So the mass density depends on the frame of the observer. So mass density not Laurent invariant. So friends, mass density is equivalent to energy momentum tensor. Is equivalent to energy momentum tensor. So rho tends to, so friends, turns out that we can generalize the mass density to a tensor called energy momentum tensor, which agreed on by all reference frames in spatial and general. Energy momentum tensor T equals to flux energy momentum term through space time. We are going to work up to it in small steps. I am going to spend about 10 minutes covering a simpler related concept called the number flux for vector starting Galilean relativity. So friends, number flux for vectors n equivalent to 10 minutes. So number flux for vectors are number 1 Galilean relativity, number 2 spatial relativity, and number 3 particle number conservation. So I will also talk about how the number flux for vector can be used to describe a conservation law for the number of particles in space-time. Energy momentum tensor, and next is energy momentum tensor. So we will see how we can use it to describe conservation laws of energy and momentum in space. So energy momentum conservation tensors T is energy momentum conservations. Number star energy momentum conservation. Energy momentum tensor for dust class perfect. Energy momentum tensors, instead of just throwing equation at you to begin, we are going to consider the number. Energy momentum tensor for dust like perfect fluid distributions of matter. Now let's start to discuss number flux for vector Galilean relativity. So friends, n tends to nt, nx, ny, nz. Time component gives the number density for a group of particles, and the spatial component give the current density for the three spatial direction. So time component give the number density time flux. This portion gives number density and number current density space flux. So friends, number current density space flux, I will explain what this means using pictures to calculate density over space. So density 1D equals to quantity tt per unit length. Charge density, example, charge density equals to charge by length. Mass density equals to mass by length. Number density equals to number per length. Current 1D, quantity passing point in unit time. Current 1D equals to quantity passing point in unit time. Electric current charge per second. Mass current, mass per second. Number current, number per. So friends, I discuss what is current and what is density. Now I will discuss 1D number density. So friends, now we discuss 1D number density. We discuss number current is equal to number divided by seconds. So we discuss 1D number density. Pick a constant time t. Pick and count number objects in a unit length del x. So friends, I have already drawn a diagram. You will see this is the et and ex, and you see that del x is, this is the del x, this is the unit del x, unit term del x, and you see that how many number, how many objects there are 4 objects, 1 2 3 4. So we see that nt is equal to number divided by del x equals to 4. Now friends, 1D number density nx, pick a constant time x and count the number objects in a unit time del t. So friends, I try to explain with a diagram I have drawn already. This is the objects is going with the constant speed, and now you see that del t is a unit time. Unit time is del t and number of object is passing through 2. So my answer is nx. My answer is nx is equal to divided by del t equals to 2D number density. 2D number density is a number of objects in unit length, and del x and del y at constant time t. This is same thing as drawing a square. This is a square at a constant time xy. This is xy plane. This is xy plane, and counting how many world lines pass through it. So if we have world line crossing the square, then we have a 2D density of 4 particles per unit area. Now if we have a bunch of particles moving in the x direction, we can find nt equals to 4, because we see that 4 number is passing through this in the area. And now we see that 2D number x current density, number objects in unit length del y in unit time del t at constant time x. So friends, I have already drawn, this is the 3-dimensional figure, and this is et, ex, ey, and the number is moving this way, and we see that four objects passing through the unit time and unit del y and del t. So taking a unit area in the time y plane at some constant x value and counting how many world lines passes through it, basically the y direction of the square is our unit length. This is our unit length. This length is our unit length. That we are counting the current density in, and the time direction of the plane is the unit time that we are using to measure the rate of flow. So counting the number of world lines that cross this plane will give us the x current density, the number of particle crossing this line per unit length in a unit of time. So friends, you will see that nx is equal to number divided by del t into del y, and we see that the number of 4 particles crossing this line per unit length. So this value is 4. I hope I can clear. Very simple way. And now we discuss 2D Y current density. 2D Y current density equals to number of objects in unit length and del x in unit time, del t at constant time. So friends, we see that Ny is equal to numbers divided by del t into del x equals to 4, because 4 element passes through unit square length. Now we discuss flux. Flux equals to current density, number of world lines that cross a unit box in a space-time diagram. In a space-time diagram, and number of particles in a unit box when one space-time coordinate is held constant. If 5 world lines enter a space-time, the 5 world line must leave. This is because particles don't created or destroyed. Let's start to discuss 3D current density. So friends, you see that this is a cube. You see, this is the length of the height of this cube is del y, length is del z, and del t is the time dimensions. So friends, this is the 4th dimension. I just create del y, del t, and del z, and 3D current density nx can be written number of particles divided by del t into del y into del z. And similarly, when in case of nz, then order of this, and del t, del y, del x, and n y is order of del t, del y, sorry, not del y, this is del x into del z. 3D current density. So, and this is the case of this diagram is for nx, and when the diagram is nz, then it is then we can take it is del x and del y, and ny. In case of ny, then it is we take del x and del z, not del y. So just replaced the dimension. Nx, ny, and nz number current density, and nt is equal to number density. It can be written del number of particle divided by del x, del y. I have drawn only second 2D dimension, but 3D dimension I will not diagram. I just show this is this way we can get this way 3D. And this is the number flux, this is the number flux 4 vector capital N. The mathematical version of the statement is that the 4-dimensional divergence of the number flux for vector is 0 given by the formula. That implies 4D divergence of flux vector n is 0. So del nt divided by del t plus del nx divided by del x plus del ny divided by del y plus del nz divided by del z equals to 0, and this portion can be written this way: del ni and del nt divided by equals to, this is called continuity equation because it relates the density of particles over time and the spatial divergence of the particle current density. Basically, if particles are leaving a spatial xyz box with positive divergence, the density of particle in the box must decrease over time, and if particles are entering an xyz box with negative divergent, the particle density must increase over the time. So friends, I have shown, this is the diagram. You will see del ni greater than 0 and del nt divided by del t less than 0. When particles are leaving a spatial xyz box with positive divergence, the density of particles in the box must decrease over time. And when particles, you see that when here particles entering, so del ni is less than 0 and del nt divided by del t greater than 0. So friends, I have already told that these facts. Now I will discuss writing continuity equation using the Einstein summation convention. Nt equals to number divided by del x del y del z equivalent to n rest number density. Nx equals to del t divided by del x, del y into del z. It can be written this way: del x divided by del t into del y into del z into del x, and it can be written this way: ux into n. Y can be written number of particle divided by del t into del x into del z equals to del y divided by del t into del x into del z into del y equals to uy into n, and nz can be written del t del x into del y. It can be written del z divided by del t into del x into del y into del z. It can be written yz into n. This is alternating way the number flux for vector in Galilean relativity. This is the same thing as ordinary number density in all frames, but we will see later in special relativity number density can change depending on the frame. Now you will notice that for the x number current density, also called x number flux, you can multiply and divide by delta x, and let us rewrite the term as the special density on the time flux time the velocity of the particles in the x directions. This portion is the velocity of the particles in the x directions. Velocity of the particle x direction. Similarly, uy is also velocity of the particle y direction, and uz is velocity of the particle z directions. We can rewrite the components of the number flux of 4 vector in terms of the rest number density. N tends to nt, nx, ny, nz equals to n into 1, n into ux, n into uy, n into uz, and it can be written this way: n into 1 into ux into uy into uz. We know that the velocities of the objects are relative and depend on the reference frame. So u dash equals to ux into ux plus uy plus uz and u. So friends, you see that u bar this coordinate, bar coordinate, also this I can write this way. Okay, two coordinate systems. Let us see a car moving in the right both stationary frame, and the car reference frame will measure the same number density of particle. So 1d the number density, pick a constant time t. Please see these pictures. This is a t bar, and count number of objects in a unit length. Then nt is equal to number of object by del t. You see that this is the 4 objects, so it is 4. If 3 objects, then it is 3 particles, then it is 3, and n bar t equals to number of object divided by del t equals to 4. Because their x basis vectors are the same, x basis vector are the same, and length don't change in Galilean relativity, and rel and length don't change in Galilean relativity. But while the stationary frame measures a current of 0. Now, while the stationary frame measures a current 0, the moving car measures a current of 2. So in this case, in this diagram, for this diagram, this is E t nx equals to divided by del t equals to 0, and nx equals to divided by del t equals to -2. Negative because particle moving left. So friends, you will see the particles moving left. That's why the value is negative. So in Galilean relativity, current measurement depend on the reference frame. Current measurement, Galilean relativity, current measurement depend on. Now friends, we discuss special theory of relativity. Special theory of relativity which uses Lorentz transformations instead of Gaussian transformations. Have to deal with length contractions. Length contractions, you will say friends in here del x, and it is half of del x. So length is contracted. So which does make the number density different in different reference frames. You will see that in here contractions is half, so number density is 2n, and it is the number density rest frame number density is n, and moving frame number density is 2n. So friends, so when the stationary frame measures a number density of 4, we will go to the diagram. We just change for the special theory of relativity. In this case of special theory of relativity, you have to draw a CT. So when the stationary frame measures a number density of 4, here the moving frame measures the number density along diagonal line of constant CT using a unit length x tilde, which results in a higher number density of around 5. 1, 2, 3, 4, 5. This is x tilde. Specifically, the number density in the rest frame is increased by multiplication by the gamma factor. For the moving frame, gamma factor takes length contractions into account so that there are more particles per unit space. So friends, we see that n tilde t equals to n gamma. Now we can also measure x current density at a line of constant x tilde and this end up being about 3, although the exact numerical values, because you see that 3 exact 1 2 3 although exact numerical value is the Galilean result of 2 multiplied by the gamma factor, which takes time dilations account. So friends, that x number current nx pick a constant position x tilde. This is the constant positions x tilde, you see it is the constant position x tilde, and number of objects in unit time del ct. So we see that del ct number of object is 3. So n tilde x is equal to number of object del ct is equal to -3, as it is moving left. It is moving left. So friends, and nx is 0 as a Galilean transformation. So we can see how to get components of the number of flux 4 vector using pictures. We can get the components using algebra in Galilean relativity. We know that 4 position vectors, and in special relativity the 4 positions vectors look s. So friends, I write, you see that Galilean relativity components, Galilean relativity is h is equal to t x y z, and n equals to number of flux is equal to n into 1 into ux uy uj. Similarly, special theorem of special relativity, h is equal to ct x y z, and capital N is equal to n into gamma c, gamma ux, gamma uy, and gamma uj. So friends, here n is equal to rest number density. We also multiply time component by c to make the unit consistent to take the effects of time dilations and length contractions into account, we need to multiply each of these component by gamma factor. Gamma factor is length of contractions. So friends, we see special relativity and Galilean relativities. Now, number of flux vector n equals to n small n into u, where n equals to number of flux vector and small n equals to rest number density. Same in all frames. And u equal to 4 velocities. Now capital N equal to, in the case of special theory of relativity, n into gamma into c into et plus ux ex plus uy plus uj ej. Capital N equals to n u, particle rest number density. N is the same in all frame. Therefore, now u tilde t equals to u tilde x, u tilde y and u tilde z equals to gamma minus gamma into beta minus gamma into beta, gamma 0 0 0 0 0 0 1 0 and 0 0 0 1 into ut ux uy and uj. This is the matrix representations. So this multiplication is this matrix is called Lorentz transformations. Special theorem, in case of special theorem, we use Lorentz transformation. Therefore, capital N equals to n into u tilde t, u tilde x, u tilde y, u tilde z equals to gamma minus gamma beta into 0, 0 minus gamma beta into gamma 0 0 0 0 1 0 0 0 0 1 n into ut into ux into uy into uj. This is equals to gamma minus gamma beta gamma 0 0 0 and 0 1 0 0 0 0 into nt nx ny. This is the transformations. Lorentz, this is the Lorentz transformation. counting the total particle, which is the single number inside a box of size 1. Because of this, the number flux 4 vector is enough to describe the flow of particle in all space-time direction. But what if wanted to count the total 4 momentum, which is vector quantity inside a box of size 1? This is the box of size 1. You will see the diagram, friends. I hope that this is the diagram, and this is the total particles in a space-time box of size. You will count, then the total particle is 1, 2, 3, 4. 4 particles in here in this box. But total 4 momentum in a space-time the box of size 1, we can count. This is the momentum of the particle. Another 4 vector is not enough to describe the flow of 4 momentum inside box. Instead, we are going to need a 4 by 4 tensors. This is the I can explain. This is the 4 by 4 tensors called the energy momentum tensors, which describes the flow of 4 component of 4 momentum in all 4 space-time dimension. So to get 4 plus 4 energy tensor, 4 plus 4 energy momentum tensor, we are going to use the same strategy of counting particles in box that we used for the number flux 4 vector, except that this time we are going to be counting 4 momentum inside of a box instead of just the number of particles inside the box. So friends, component of energy momentum tensor T alpha beta equals to flux of alpha momentum going through a unit box of constant beta. Now you will see this diagram. We can express energy density Tt and Ttx and Tty, Ttj. This is energy flux, and momentum density is this. So friends, these discussions we just explain flux overlines that cross a unit box in a space-time diagram. We have learned number density, we have learned number flux for vectors. So friends, I will publish the next video, and I will try to complete the total energy momentum tensors. I will complete. So friends, I hope that I can clear this concept. I will publish very soon another video. So thanks for watching.